So our next speaker is Jacob from Chalmers University of Technology in Sweden, and the presentation is titled the Interval-Asynchrony, the limited intervals of localized asynchrony for fast parallel SGD.
Yeah, thank you very much. Good afternoon. As he said, I'm Jacob, and I'm going to be presenting our recent work on speeding up deep neural network training using many core CPU shared memory systems. So this work was co-authored with Philip Lastsinas. So in this presentation, first I'll talk about the problem that we set out to try and solve. And then I'll give some brief background information on, first of all, what stochastic gradient descent is, and how you can use this algorithm to train a neural network, just in case anyone isn't familiar already. And then I'll talk about two different ways that you can parallelize this and use multiple CPUs to scale this up. And I'll talk about the pros and cons of each of those, which will motivate our method, Interval-Asynchrony, which I will describe and then present the results and evaluation of. So yeah, first of all, the problem. So it's quite unsurprising to say, I think, that machine learning is becoming an increasingly important part of life in general, for better or for worse. And the problem is that the machine learning model is only really as good as the quantity of training data or the size and the complexity of the model. And increasing either of these things inevitably will increase the time it takes to train the model. So if we can train the model better, it sort of follows that we can reach better models, essentially. So if we want to train a model on a CPU system, the logical way to speed this up is use more CPUs, essentially. But if you use more CPUs, you have to somehow decide how these CPUs will communicate with each other to perform the training process. And you can do this synchronously or asynchronously, and both of these have pros and cons, which I'll go over in a minute. So what we wanted to do was we wanted to see if we can improve the scalability of deep neural network training on a CPU system while maintaining good accuracy. So yeah, as I mentioned, first of all, we can talk about a very brief introduction to gradient descent, which is the core of the stochastic gradient descent algorithm. Let's say we have a function L, and this represents essentially the performance of our model, given some parameters theta. We want to minimize L, because we set up this function so that when L is lower, the model tends to be better. The way this algorithm works is we pick an initial arbitrary value of the parameters, which we call theta, and that's this black dot at the top right. And then we calculate the gradient, and then we essentially adjust theta in the opposite direction to the gradient, like this. And the idea is that we essentially want to descend down the slope, assuming that this function is relatively smooth. And if we iterate this process a few times, ideally we get closer to convergence, by which I mean the algorithm will finish because the model is relatively good. So if we want to actually use more, previously this was just like a sequential algorithm, right? We have sequential iterations. But if we want to use more threads to compute this, there are two broad categories in which you can sort of place different algorithms. The first is synchronous, and in this case, let's say we have three threads. Each thread, in parallel, of course, will calculate a gradient. And to calculate a gradient, this is done by taking a batch of training data, and you can use some algorithm essentially to estimate the gradient of the loss function with respect to this batch of data. So each thread calculates a gradient, and then you just wait, and then once every thread has finished this computation, you average those gradients, and you apply that to the global model. And you can run this process over and over again, as before. And you can see that we get a relatively good convergence here. This is a really nice way of doing things because, as you might notice, we're essentially doing the exact same computations as we were in the sequential version. It's just that we're splitting them up over a number of threads. So we can potentially get some performance gain, but we're not losing any accuracy at all. It's the sequential semantics. However, you'll notice that if the threads take different amounts of time each to compute one gradient, then the faster threads will spend some extra time waiting for the slower threads. And this introduces a bottleneck into the trading process. This is unsurprisingly only exacerbated with more threads. So you might think, okay, then what if we just remove the synchronization and we can do it asynchronously? So now we will start from some value of theta here. And again, all of the threads begin computing a gradient based on a mini batch of data in parallel. But now we can say that thread 1 finishes first, and let's just say it doesn't have to wait for the other one, so it can immediately apply its update to the model, like this. But the other two started computing their gradients based on the initial value of the parameters, right? So when the next thread finishes its computation, the blue one, it uses the gradient that was based on an outdated view of the global model and applies it to a later view. So intuitively, you can maybe see that this kind of, this is not so accurate because the gradient wasn't designed to update this model, it was designed to update the initial model. So we call this kind of update a stale update, and the staleness of an update is nothing more than the number of times the shared model has been updated since the gradient began to be computed and the time at which it was actually applied to the model. But it still works quite well. You can see this next update, this was based on this initial red update, and it's not really very accurate. But in the end, it doesn't matter too much because we do still get closer to convergence and we do actually reach there. But then maybe we will overshoot a little bit and it just won't be so accurate. And the reason we overshoot is maybe we're applying gradients too late, essentially. So it maybe takes more, we have stale updates which tend to be less accurate. And this means that it may take more SGD steps to actually reach a good accuracy of the model. But on the other hand, we save a lot of time because the threads don't have to wait for each other. And the amount of time you save increases with more threads. So, okay, we thought maybe we can propose something like a semi-asynchronous scheme, which essentially will change the degree to which it's asynchronous constantly throughout the runtime of the execution. And the logic here is that maybe if we do not fully synchronous and not fully asynchronous, we can somewhat get the best of both worlds of maybe we can get the throughput of asynchronous and the accuracy of synchronous. The motivation behind adapting how asynchronous this algorithm is throughout the algorithm comes from the fact that it turns out the impact of staleness is not constant, and it's way worse to have stale updates as you get closer to convergence, because at this point you need to sort of fine-tune the model a little bit. So our algorithm looks like this. We have a timeline on the right, which works exactly like the timelines we just saw. The y-axis descending is time. And essentially what we do is we split up the whole timeline into a number of what we call asynchronous intervals. And an asynchronous interval is defined, it's only defined by the number of SGD steps that have updated the model in that interval. So in this case, the interval size is 8, and as you can see, we have 8 shaded in updates here. The point is that we allow SGD to run fully asynchronously within an interval, but we don't allow updates to cross interval borders. So you can see that this step, which is labeled reject, has crossed between this interval and the next interval. Therefore, it was rejected, and by reject we just mean it was discarded. Its gradient was not used to update the model at all. So the important thing to note is that the size of the interval, in this case it's 8, it can be anything, any integer anyway, and we're allowed to change this at any point dynamically during the runtime. So this is really useful for the reason that I previously mentioned, and specifically the algorithm that we introduced to update this interval size is also very efficient, so you can do this with minimal overhead. So let's look at actually the effect of changing this interval size. The plot on the, well, both plots have an x-axis of the interval size, right? So 64 to 1024. Note that when we say interval size of infinity, this is identical to a fully asynchronous execution, right? So this is intuitive, hopefully. The plot on the left shows that as we decrease the asynchronous interval size, we also see a decrease in the expected staleness of any given update in that period of time. So when we say E tau, tau is the symbol we use to refer to staleness. So yeah, we get an almost linear, exponential decrease here. The second plot shows that as we increase the interval size, we actually, unsurprisingly, we have a higher proportion of steps that are accepted. And the logic here is that if you have a larger interval, you have more steps within this interval that don't overlap boundaries. If you have a smaller one, then many more of the steps will begin in one and end in the next. Right? This kind of makes sense. Of course, we want to reduce the, or we want to increase the amount of steps that are accepted as much as possible, because otherwise we'll have a lot of wasted work. But we also want to decrease the amount of staleness. So how can we actually adjust the interval size dynamically in some intelligent way, hopefully, in order to best manage this trade-off, given what I previously said, that the impact of staleness is greater closer to convergence. So we proposed two different methods, one called decay and one called probing. And the first, decay, is a little bit similar to some previous methods commonly used in machine learning. For example, it's not uncommon to adjust the learning rate on a gradient. We do something quite similar where we say, okay, begin with an interval size of whatever, and then just decrease this gradually with a fixed gradient with respect to a number of steps. So this works really well, and it makes sense, right? Because this means that nearer the end of the algorithm, the interval size will be smaller, and this corresponds to reduced staleness, which is exactly what we want. The difficulty here, as I'm sure you're thinking, is that, okay, how do we actually pick the gradient? And it is difficult. There's no, this is a problem. It introduces a new hyperparameter. We do propose a value for the gradient in the paper, which works for all of the tests that we try. However, if you want a more automatic approach for adjusting the interval size, you can try option 2, which we call probing. And this is sort of an online method of dynamically sampling nearby values of the interval size, which we call y, by the way. And then, so we'll essentially do a little bit of execution at different values for the interval size, and then measure how the convergence rate depends on that value. And then we'll pick the one with the best convergence rate, by which I mean the one which has decreased the model loss the most in a fixed amount of time. And then we'll pick this for a slightly longer period of execution for then starting another probing phase. So this is a more automatic method. Both of them work well, as we will see in the evaluation. So speaking of the evaluation, we wanted to answer two main questions in this paper. And the first of these is, does our method, Interval-Asynchrony, is it able to train a deep neural network model to an acceptable accuracy faster than previous methods? And the second one is, does it scale well? Which, by scaling well, I mean it's able to make use of a larger number of threads without suffering with lower accuracy, and actually, hopefully, being able to utilize these threads to increase the training time. So let's first look at this table, and it's a little bit dense, but at least I've removed half of it, so you'll have to see the paper for that. The main point here that I want to get across is this. This middle column shows the time that the 4 different training algorithms take to train a specific deep neural network to an accuracy of at least 50.9%. we picked this threshold. It's the highest accuracy that all of the algorithms achieve in most cases. In some cases, some of the baselines didn't manage, and it's fine. So first, let's look at the actual algorithms that we compared against. First of all, sync and async. These correspond to this fully synchronous and fully asynchronous methods that I mentioned a few minutes ago at the beginning of this presentation. And then we also compared to this one called L-async, which stands for elastic asynchrony. This is a recent work which set out to achieve a similar goal to us. And the way that they approached this was they thought, okay, well, you can reduce the number of threads instead of anything else. You can just reduce the number of threads, and this reduces the staleness. So L-async is a fully asynchronous method which dynamically adjusts the number of threads in a similar way to how we dynamically adjust the interval size. So this made sense as one to compare against. Now this highlighted column here shows that our method to train a model to this 50.9% value is, for one thing, it's way faster than synchronous because, as I mentioned earlier, synchronous, when you get to a large number of threads, it has this huge bottleneck where you just can't make use of them very easily. But if we compare the three asynchronous methods, ours is significantly faster, up to nearly half the time in the best case, but in general it's just way faster. The other thing to note is that we don't lose much accuracy. I mean, this is the average best case accuracy and the best case accuracy across the various sets of parameters that we considered. And you can see that our asynchronous method, or our semi-asynchronous method, achieves a better accuracy in the average case than the other asynchronous methods. Not quite as good as the accuracy achieved by the synchronous algorithm, but this is to be expected. That's almost like the sort of ideal case. So I would say this covers the first of our evaluation questions in that we do achieve an acceptable accuracy significantly faster than other methods. Now let's look at scalability. So this plot is slightly, maybe a bit complex when you first look at it, but we have two rows here. Like the first row shows how the accuracy achieved by the different training algorithms varies as we increase the number of threads, which is the x-axis. And then the second row shows how the time taken to reach a given threshold accuracy varies with the number of threads. Okay, so we tried 32 to 128 threads. This is the highest number of threads we could attempt based on the machine we have without doing inter-socket stuff. So the important takeaway here is that the blue and the green lines, these are the two asynchronous baselines. Blue is fully asynchronous, green is the L-async. And if we look at this top plot, we can see that as we increase the number of threads, the two asynchronous baselines drastically fall off in terms of the accuracy that they're able to achieve. Even though they're able to achieve this faster, as you use more threads, they don't reach as high an accuracy because of this asynchrony-induced noise due to the staleness that we saw earlier. Whereas our one, some of the parameter combinations drop off a little bit, but in general it's nowhere near as bad as the baseline cases, and in some cases we maintain the same accuracy for all number of threads. So this essentially goes to show that our method is able to handle scaling to a large number of threads a lot more nicely than baselines. And one more thing to mention here. You can see that, for example, you may be concerned that the green and the blue lines on the bottom plot do reach the threshold accuracy a little bit faster than our algorithm in many cases, actually. But then you need to look and say, well, even though it's reaching this accuracy a few seconds faster or so, the actual accuracy that it achieves at the end of its training is way lower. So anyway, based on that, we argue that our algorithm is significantly better at scaling to a large number of threads than these two baselines. And as we've already shown, it also is able to achieve this accuracy a lot faster. So yeah, just to conclude, we've introduced a new algorithm for scheduling SGD threads in a semi-synchronous way. And we propose two different methods to adjust the hyperparameter which our synchronization method introduces, which is the interval size. We evaluated these two methods and showed that they both are quite effective. And we also demonstrated the superior scalability of our method compared to the aforementioned baseline approaches. So that's all. Thank you for listening.
Thank you for the very nice presentation. Do we have any question for the audience? Yeah.
So I have two questions.
Yeah.
One, specifically, you had one question. One is on the specific parameters probing and decay, right?
Yes, back here.
Yeah. So
Yeah.
the question is, which thread is any specific thread will do, or all threads will do? That's
Yeah.
one question. And the second question is a little bit more generic. When we have GPUs be able to do this quite effectively, why do we have to focus on CPUs?
Okay. Yeah, great question. Yeah, it's a good question. I'll answer them in order. So first of all, your question is, with decay and with probing.
Probing.
Yeah, with probing you're saying, do all of the threads take part in this probing? And the answer is yes, they do, because we want to evaluate the effectiveness of the interval size in the specific setting that it will actually be run. So we need to use all of the threads. We did do some work relating to what you're saying on if you have, like, for example, I mean, our system has two CPUs in two sockets, and we were thinking, okay, well, we're only using 128 threads maximum here, so if we have another socket with 128 threads, then yeah, we could essentially do this probing at the same time as the execution. So it's a good point, yeah. But right now we're not. And then to answer your second question, which is, why do we want to look into training neural networks on CPUs when we can do it very quickly on GPUs? There are certain types of problem where actually CPU training can achieve faster training times than CPUs. But the other reason is that CPUs are there are a lot of cases where you have a CPU available, and maybe you can have a large, many core CPU, but you don't have.
GPUs are expensive.
Yeah, exactly. GPUs are expensive. So it's for these two reasons, essentially. And actually, maybe one more reason. We wanted to look into asynchrony, and my understanding, at least, is that asynchronous algorithms on GPUs are slightly less efficient because you want the different threads on a GPU to be doing sort of stuff in lockstep. So we wanted to look into asynchrony as well. Yeah. So thank you for the questions. Yeah.
One question. If I understand correctly, both these methods rely on decreasing the size of the window over the time because you need more precision in the end.
Essentially, yeah.
So, in the end, isn't it better to switch to the synchronous execution? Because if you just have a very small window, then you're just rejecting most of the work you're doing. And in that case, it might be better just to switch off the threads because the one core that remains may boost up or something.
Yeah, actually, this is a really good point, and it's something that we want to look at in the future. Yeah, I think this will be quite effective. And in fact, if we go back to maybe this table can demonstrate what I mean. If we look at the row for the L async, which is actually changing the number of active threads, we can see that in the best case, it achieved a really good accuracy. And this was actually a case where its algorithm did reduce the number of threads to be maybe 2 or 3 or something. So it was close to a synchronous execution. And that sort of goes to show that, yeah, it can increase the accuracy a lot. Thanks.
Okay. Thanks again. So, okay. I invite the next speaker, which is Matthew Teifonei from Zurich National Supercomputing Center. The title of the presentation is Robustness of Deep Learning Classification to Adversarial Inputs on GPUs. Asynchronous parallel accumulation is a source of vulnerability. Welcome.